Hey, good to see you again. All right, so we're now talking about acceleration. So this is grade 11 university level physics, unit 1, lesson 4. So we're going to actually, we talked about acceleration a little bit in as a slope of a VT graph, right? The acceleration, we already know what it is, kind of. It's a rate of change of velocity. But we're going to talk about it now a little bit more mathematically, just to come up with some formulas so we can put them all together and we can have a nice little way that we can calculate things. So we already know that acceleration is the rate of change of velocity with respect to time. Right? Also, we did say this before, but just a reminder that it's a vector quantity. Remember what a vector quantity means? Remember that has to have a direction as well as a magnitude. Vectors have direction and magnitude. And we can calculate average acceleration over a certain time interval delta t just the way we would calculate average velocity. But instead of positions, we're going to talk about velocities. So it's the difference in the velocity, delta v, v2 minus v1, divided by that time interval. Right? And we already talked about this, but the SI unit is going to be meters per second squared, because this is the top here is going to be meters per second, and we're going to divide by seconds. So that's going to give us meters per second, or per second squared. Right? When we talk about acceleration, let's say we say it's accelerating at 1 meter per second squared. That means that for every second, its speed or velocity increases by 1 meter per second. Right? So let's talk about gravity, for example. Gravity is about 10 meter per second squared. You drop an object, every second, its speed increases by 10 meters per second. Okay, that's what that means when we say meter per second per second. Every 1 second, its speed changes by that many meters per second. Okay, and again, that's one of these derived units that has meters and seconds in it. So the SI unit is meter per second squared. Let's do a quick little example here. So a car accelerates from rest and reaches a speed of 18 meters per second west. Speed, that should be velocity. Mr. Stone, that's a velocity. It has direction. Jeepers. In 6.2 seconds. Determine its average acceleration over that 6.2 seconds. So what do we know? We know that its second velocity, the velocity at the end of the interval, v2, is 18 meters per second west. We know it took 6.2 seconds. And we can also infer from this, because it says from rest, very important word there, from rest, that its initial velocity, its v1, is 0. And they're asking us to find the acceleration. So we take our new formula we have, v2 minus v1 all divided by delta t. We substitute in our pieces, and we solve. And we get 2.9 meters per second squared, right? Because this was meters per second, take away meters per second, so the numerator is meter per second west, and divided by seconds, so we're going to get another second in the denominator. And just keep in mind that because we had west in the numerator, our answer is also going to be west. So we can, put a nice little a therefore statement at the end saying that the car accelerates at 2.9 meters per second west, right? Now, what about the other direction? What happens if we take that car now, we've sped it up to 18 meters per second west, but now it has to stop. And instead of taking 6.2 seconds, it's going to take less time. It's going to take 5.4 seconds to stop. What's its acceleration now? So in this case, it's a little bit backwards because it's starting off with a speed of 18 meters per second west. That's the v1. And the time interval it takes to stop is going to be 5.2 seconds. But this time, it's going to end up with a final velocity of v2. And then we're asked again to find the acceleration. What's this going to do to our problem? Once we substitute in, we're going to have 0 take away 18 meters per second west. So now we're going to end up with a negative number in our answer. So we have a negative acceleration in the westerly direction, which means we are slowing down, right? Because the car was traveling west. So then if we have a negative acceleration, the opposite direction to its velocity. It slows down. Another way we can say this is that it has acceleration of 3.3 meters per second squared east, the opposite direction, right? Remember, it was started off traveling 18 meters per second west, and then it's going to end up slowing down. Every second, it's going to lose 3.3 meters per second. So after 1 second, its new speed would be what? 14.7 meters per second, and then 11.4 meters per second, and so on and so forth, until after 5.4 seconds, it'll have stopped. Okay, and remember, what's the last thing we have to do? Yell it into your microphone or camera. I can't hear you through the interwebs. Come on, what is it? No. The car accelerates at 3.3 meters per second east. And remember that this is in the opposite direction of its initial velocity. So this is a slowing down, which makes sense because tells us the car is stopping, right? So it has to slow down. And that's where that negative showed up in our math. Okay, that's the beautiful part about all these physical problems that we're going to deal with. We're going to get mathematical results that have physical meaning, and we're going to have to think about those. So we got a negative result, and we had to understand what that negative means. In this case, it's slowing. All right, another example, number 2. This is an interesting idea. Anytime we're going to have to talk about acceleration, we're going to have to talk about gravity. All right, gravity, anything that falls, anything that's under the influence of gravity on Earth, important, it's on Earth, close to the Earth's surface, accelerates at a rate of 9.81 meters per second squared. You need to memorize that number. That's a very, very important number. That's what we call g, lowercase g. This is the acceleration due to gravity. All objects, doesn't matter how heavy objects are or small they are, anything near the Earth's surface will accelerate at approximately 10 meters per second squared. Every time a second goes on, it'll increase by 10 meters per second. Now, we don't really see that too often because we have air resistance, and that slows things down. So when somebody drops a piece of paper compared to an eraser, we know that the eraser is going to fall faster. And that's only because of the air resistances in the way. The amount of stuff, the amount of particles, there's all these oxygen and nitrogen molecules all hanging out underneath that paper. And because the paper has such a large surface area, all those molecules are bouncing off of it, and it's slowing it down. The eraser, if it falls for long enough, it'll reach a terminal velocity, a maximum speed, where the resistance of air takes over and it slows down. It's just that the terminal velocity of an eraser is much, much, much higher than the terminal velocity of a piece of paper. So when we drop a piece of paper in an eraser, we know that the paper is going to drop much slower. But what would happen if we removed all the air? Let's see, let's watch for example here. So let's say this is a bowling ball and some feathers. They're dropped, and it's exactly what you would expect. There's air here. Bowling ball falls right away. All right, it's very, very quickly. There's not much air resistance. It's going to come crashing down. The feathers, on the other hand, are slowly going to float their way down. Right? This is what we would expect. But now the question is, what would happen if I repeated this experiment here, but I took all the air out? This video is taken in a NASA facility where you can remove all the air. There's actually about 50 tons of air in this hangar, and they remove it all. And watch what happens when the two objects fall. Now that you can still see there's a little bit of air. It's not a perfect vacuum. There's still some motion in the feathers. They still curl up a bit. But the feathers fall at the same rate as the bowling ball. They're both falling at about 10 meters per second squared. Okay? That's an amazing video. See, they land at the exact same time. But because of the air, we don't really see this too often. But feathers in a bowling ball, any object, it doesn't matter what it is. We'll talk about this in the next unit. It doesn't matter what the object is, it'll always fall at that 9.81 meters per second down. Okay? Let's go back to the problem. Sorry. It falls for 8.2 seconds, right? You take a timer and you time how long something falls. How fast is it traveling when it hits the ground? So what do we know? We can take our formula. Now, it's asking us for how fast it is, right? So we want the unknown in this case now is going to be our delta V, our change in velocity. In this case, because it starts at rest, it's dropped. It's going to start at rest. The change in velocity is going to also be equal to, right, delta V, is equal to V2 minus V1. But in this case, V1 is 0. So that's gone. So we're just left with the change in velocity is just equal to the new velocity at the end. So really, I could have written, I should put arrows on these guys. They're vectors, right? So if I solve, I'm going to multiply both sides by delta t. And they're going to cancel here. So the new velocity, or the change in velocity, is going to be a, the acceleration, times the time. There's a new equation there for you. If I replace the acceleration and the time, the acceleration was 9.81 meter per second down. The time is 8.2 seconds. I'm going to end up with 80.44 meter per second. Now, why does that happen? Careful here. Meters per second squared multiplied by seconds. I'm going to cancel one of them. I'm left with meter per second. So rounding it to 2 decimal places, because 8.2 has 2 significant digits. Sorry, 2 significant digits. Rounding it to 2 significant digits. I end up with the final answer of delta V equals 80 meter per second down. And just, write a therefore statement and we're finished the problem. All right, so these are pretty straightforward. So try some of these problems. I apologize, this should say V2 minus V1. I hope it's not messed up like that on the PDF. Again, these are all on the Weebly. Pretty straightforward problems. Solutions are also on the Weebly. Okay, so best of luck. Again, stay safe, and I'll be talking to you later.